what we talking about, that's an analog complex, but the DNP sample, if you freeze it up. We're acting like we're supposed to GQP, but we never do.
Actually, it's precise. If you can find, and
Yeah,
you said you're one of your name. It's okay. It's better.
This actually.
And so our condition has a predicate function.
okay, you guys good with just starting now? I recorded yesterday. I'm supposed to be recording.
It is recording.
How do you see that?
This monitor.
You can see it.
Yeah.
So we got all that 10 minutes of chit chat.
I suppose.
Let's start. All right, so this is what we're doing today. Yesterday, we talked about conditions where you could create an effective Hamiltonian that's just heteronuclear dipole coupling. It involved putting two spin locks on and adjusting their powers so as to be a matching condition. The matching condition, I think, is most clearly seen in this doubly rotating frame that we spent most of the class talking about, so that these terms in the dipole coupling have two different time dependencies, one because of the pulse you put on I spin, the other because of the pulse you put on S spin. If those are two arbitrary frequencies, the average of those functions will be 0. If those two frequencies are matched, the average of the function will be 1/2. So that's a way to keep that term. And then yesterday we went in great detail. What have we done with the other terms? And it's various tricks to make them seem like they're 0, which don't work perfectly, but they work well enough that this experiment overall works. Okay, so that's where we left it. We have a Hamiltonian. Looks like this, no time dependence because we've averaged it. Okay, yeah, please.
It looked very different from the original heteronuclear type or something. Does that mean that that's an artifact? Like we have to get rid of the IYSY somehow?
We're going to use them.
Okay.
We're going to figure out, and this is towards the end of the lecture, what part of that so-called dipolar alphabet, which is just like decomposing the dipole coupling in terms of looking like raising and lowering operators, what part of that is this? We're going to fish out what we want from it. Okay, but we also have an assumption about what our initial polarization is. So if you have an initial polarization and you have an average or effective Hamiltonian, then your interest normally is in predicting the future using a time-dependent Schrodinger equation written in terms of a density. So we want this. And then I think I ended by saying, I'm going to show a common trick how to do that for especially simple cases. And it covers most of the cases you will have thought about in solution NMR. It's a rule that can be extended to many other cases, but you'll recognize in it almost everything we've already done. So, and this is called the Baker's-Hausdorff-Campbell expression. And if it just happens to be true that the initial density matrix, you take a commutator of your Hamiltonian with it, you get something that isn't it. It's not rho, it's not H, it's not 0. You get some other thing, okay? Now take that other thing and take one more commutator with the same Hamiltonian. For many cases, but not all, you'll discover that the resultant is proportional to the original density matrix. And what that'll turn out to mean in terms of dynamics of evolution is that you're going to oscillate between rho and this other thing, and then back to rho, and then to this other thing. That there are really only two kinds of coherences that pop up in this system. You start with rho naught, you make something else out of it, and when that thing decays, you come back to rho naught. If this double commutator obeys this equation, it's a little bit like a differential equation for a spring or a swing or whatever. It's a little bit analogous to that. So the second commutator being proportional to the original density matrix is what? Is good. It's a good experiment. And then you can write closed form expression for all time. But, you know, of course, you've always ignored some things. You didn't put any relaxation in, you didn't put any other, you know, lossy terms. But it's an elegant thing to be aware of. So where did we get that from? I'm not going to do like a full derivation because we just have today, but I'm going to give you a taste of why do we know that? Why do we know if that double commutator obeys that rule that you can write this elegant little solution? And actually, before I do that, can I just take a minute to support the idea that this actually covers many cases you've already seen. So can you think of a case that's simple in NMR that you feel comfortable with? Like, you start with this density matrix, you apply this thing, and then you end up with a resultant that you just feel like you know from memory at this point. Just pick something that you feel comfortable with. What's rho naught? Okay, rho naught is IZ. Oh, I erase this. Sometimes when I try to rotate this, bad things happen. Nothing bad's gonna happen if I just turn it around, but like. Now you're supposed to rotate it. So what do? You like unscrew it a little bit? Is that the right thing? Thanks. Did I go wrong? If I break it, the staff here, that would be nice. Okay. It just looks like something Art might need again, that also looks. Okay, here we go. Yorktown address? No, right? Huh. Oh dear. We got any spray? Wow. All right, well, I'll just write, this is so simple what we have to do. So rho naught, what did you want? I what? IZ? That's a great one. And then what's H?
Omega 1 IY.
All right, so first thing we need to calculate is H rho naught. What's that? Put H bar omega on the outside. Then I can just have IY IZ. You know what that is?
Minus one.
IX or minus X?
X, I guess, yeah,
IX, yeah. All right, so then I want to take this whole thing. I'm going to give this a nickname. I call this R1. Then I'm going to calculate R2, which is the onto R1. And that is going to be Hamiltonian is still IY, but I got to put H bar and omega out here, right? And then I take the commutator with that resultant. And what do I get?
Minus.
IZ. But I don't want to lose these.
Yeah. Squares.
Omega squared, and we always ignore these H bars. All right, so look at that. Rho naught was IZ, and this R2 is a scaled version of IZ. And we know what happens in that. If we have a Y pulse, we make great circles, and we go by way of X, and then minus Z, and then back. So that's an example, but everything that we do, or much of what we do can be cast in this way. That you have an initial magnetization, You have an average Hamiltonian and you make some sort of a great circle. The question is, it's not gonna always be so simple as one Cartesian. And you can recognize that your problem has that formula by taking this double Hamiltonian. So I think that's a little different than how it was presented before, right? You have these oscillatories, and it's that double commutator of the Hamiltonian that's your clue as to where the magnetization might go and how it might behave over time. And what is the frequency of that? And you just see it all by just simply taking that commutator with the Hamiltonian. Now, why do we know that? What kind of a derivation stands behind this expression? I'm going to skip some steps, but I hope I give you just a taste of it so that if you wanted to, you could go home and do it for yourself. So this calculation is never that easy. There are different ways you're going to go about exponentiating something that's actually in a matrix form. You could diagonalize that matrix. You could do a Taylor's expansion. Those are your two main routes. You could just do it numerically. You know which approximations, or if you have a lot of computer time. So this is the expansion approach. In some other part of the class, if we do the dynamics part, we'll talk about the diagonalization approach, which is mostly not smart, not fast, not compute intensive. I just find it elegant. But this is like maybe the more common thing somebody would think of. Just take an exponentiated Hamiltonian and write it out using this rule. So that would be an application of a Taylor series expansion. Now, what happened before in the class where you used this already? I think a couple of things happened already in art section. Remember this? It happens in Redfield, and it also think happened early in the class, related with interconverting e to the ix and sines and cosines in some way. But so we're using this, and I just want you to notice that it's a trick that just comes up over and over again in spectroscopy. So that's what we're going to do to write out the e to the minus it and the e to the it, okay? H bar g. All right, so if you do that, you get this kind of expression for the exponent propagation, that kind of an expression. And you need to use that for before and after rho naught. The leading term is 1. So when you make the whole sandwich or calculate the whole thing out, the leading term of the whole thing will just be 1 times rho naught times 1. And that's intuitive. And then you get two terms that look like minus IHT times rho naught or rho naught times IHT. So there's your first commutator, comes out of the second order term. And the same kind of symmetry is going to apply for every other term. So all of the other terms, you'll end up with something that looks like a commutator type format. So that expansion comes from just a Taylor's expansion of the exponent. Now, I had these nicknames, and I'll just say this what I was at the board. I call this R1, and if I take the commutator of H with R1, I'll call it R2, and so on and so on. And it happens from the expansion that you get these prefactors. Factorial. Actually, that should say 1 over 3 factorial, isn't it? Yeah. So, what's that good for? We're not there. We're halfway there. Now, let's take the presupposition that we're working with, that R2 is omega squared times rho naught. If that's true, then R3 has to be omega squared R1, and R4 has to be omega squared R2. There should be an omega squared there. So we can use that they will all have those sort of recursive relations. And that means that I can group all terms as being proportional to either rho naught or R1. So I can just rewrite that series in this way. And when I do that, I notice that this is the same as the series expansion for cos omega t. And this is the same as the series expansion sine. And I think if you look back in some of the early notes from where he had something quite analogous to this for another problem solution NMR. I'm just not putting my finger on the name of one that came up in class, but you'll see that this has been used before. And it comes up regularly in NMR. So this Baker's Halter Campbell, this is a kind of elegant summary of that kind of thinking. You just have to check the commutator and then you know you can write this sine and cosine expression. Now, there's a different special case that sometimes comes up. Like maybe this isn't true. Maybe it doesn't work that R2 is a scaled version of rho naught. But maybe the next term behaves that way. Maybe H commutator with R1 is a scaled version of R1. So R3 and R1 have this special relationship. That means that starting from that term, all the rest of them will also. And then you get a modified useful rule. And that happens to be the case for our problem. So instead of that nice, elegant little one, you have rho naught, and then you generate this, and then you generate this, and then you go around in a circle. So you can imagine a yet more complicated case where that relationship doesn't appear until the third term. Actually, I don't know an example of that, but this is an example of this kind of pattern. And so that's what can be used here. I don't know if I really worked this all the way through, or I think maybe I have some notes where it's all the way worked through and I've left it as an exercise to you, but you see it rho naught. You see the dipole. So take those two, the first commutator, the second, the third, and you'll see pattern. And so you end up with an expression that looks like this for the evolution. So your initial magnetization. Another term that's really interesting, that's the other spin without any complication. It's just the one spin operator. That's what we want out of the dipole couple. We want at an early time to have just IX, and at some later point have mostly or all of that converted to SX. And then there is this undetectable magnetization that you go by way of, or not directly detectable. One of the things to think about in these kind of transfer experiments, it comes up in all of them, but we don't always draw attention to it. If you're doing this kind of transfer and you're in the rotating frame, then the things that will determine your success are not T2, they are T1 rho of X, SX, IX, and of these funny coherences. So now if you want to be really, detail oriented about the whole thing, you should get interested in relaxation rates of undetectable coherences. An old paper about this that we were involved with for the rotational resonance experiment. But it's probably not the big driver of what experiment you pick. It's probably more of a detail, but on the other hand, these losses, they kind of rule your world. Like they take your signal away from you. So interesting if we could have more control over them. Okay, so now we can see the coherences oscillating in time.
Here, if I choose my initial density matrix to be IY instead of IA.
What would be different?
Yeah, so you could commute with that IY/SY part of average dipole. It would evolve exclusively under ICSC, is that correct?
Yeah.
But would it lead to like antiphase coherence of the other spin, and is that why I don't want to?
I have to do a little calculation to be sure, but I think two things are true. I think you would no longer have the self-decoupling effect from the pulse, because instead of spin locking, you're doing these large Rabi circles.
Oh, I see.
And so I think that allows some of the homonuclear couplings to creep back in more. The other thing that I think is true is that now if you only have an IZSC type operator and no X's and Y's, that it might be a little bit more akin to a TDOR experiment where you're dephasing across Z and making use of that, but you're not really pumping the raising or lowering operators. So is that bad? Is that worse? Which one actually could give you the most of what you want at the end in the shortest amount of time? I'm not sure. I think this is the better choice, but it's a good question. Okay, now there are a couple of things that we need to put back into the problem to have a more realistic description of what we actually do in experiments. Frequently, irradiation is not on resonance. We had on resonance irradiation in that model. And then we said, well, if there is a chemical shift offset, it'll just average to 0. But here's something where we're going to treat the fact that it's off resonance. If it's not just a little bit off resonance, we're going to treat it explicitly and see what it leads to. Being off resonance leads to a lot of flexibility in setting up the transfer conditions, because remember that the effective field depends on both the offset and the actual field strength. So by going off resonance, you can kind of tune your field up or down. It's just another control that you have, and it turns out to be useful in a way that I'll mention in a second. I guess I don't have a slide, but I'll tell you at the board. So you got to think about the offset in terms of the effective field, and it's the effective field that you match in this experiment. It's the effective field and not omega-1 that you match when you're off resonance. And it'll be more clear after the next couple of slides, but you're always rotating around the total field, the effective field, right? You can't have two fields on and then you say, oh, but I have a funny spin, it's only listening to this. No, if you have two fields, it's going to go around both of them, the sum of both of them. And that matching condition that we talked about yesterday, where we have to match I and S, both of those should be the effective field, not omega-1. So for that reason alone, we have to talk about offset. But there's also a nice trick in how to sort of formally treat the situation when you have an effective field that we're going to go over right now. Okay, so instead of a frame transformation that's around B1, maybe a better idea to do a frame transformation that's around the actual effective field, if there's an offset. And we didn't do that in the first treatment. So let's think for a minute how we could do that. Because we want to remove as many parts of the field as we can, right? So let's do a frame transformation around the whole effective field. So to do that, what you do is two frame transformations. The first thing is you jump into a tilted axis system. That's like a once and done frame transformation. So you started out with this being Z. And now I want this to be my Z axis. You also could have used this as Z when you were decomposing and saying the CS is one term and this is another term. But now we're going to say, we're going to talk about the effective field, the whole field. So I kind of like that effective field axis to be my Z axis. So that's a tilt the axis transformation, just a tip, rotation around Y. So you're moving your Z axis, one thing, and it's not time dependent. Through an angled arctan. So interaction frame transformation will then be a rotation around that new axis. That will be your interaction frame, and that will be time dependent. Right, so we have this one tilted frame transformation, not time dependent, just a one angle, and then this time dependent transformation around the effective field to represent the bucking field or remove the CW. Okay. The two transformations. So this is going to be a toggling frame that follows the net action of both RF spin locks and corrections for both frequency offsets. Now, a lot of times it's only one of them that's off resonance and the other one is treated as on resonance. And that might be the case, I can't remember, in the last slides that I had. Now, let's just take a minute and say, why are we doing this? We want to transfer from N to C. And C, and so that nitrogen, of course, has a coupling to its own C alpha, beta, and so on. And then it might have coupling back to the preceding carbon. So you might have an experiment in which you've gotten your magnetization from H to N on one CP, and now you're sitting at this junction that you want to move from N, for example, to see what's out on the side chain. And if you turn down the power on the carbon channel, which we do for many reasons, as we were talking about yesterday, some of them are not that clear, but this is clear. I might turn it down so that this guy is at 175 ppm, and this one is probably at 60 ppm. And if I turn the power down below about 8 kilohertz or so, then I can make it on resonance, match the condition for this guy, and be pretty far off for this. So that's a difference of 100 parts per million. If carbon is 200 megahertz on a really high field instrument, you know, that's 20 kilohertz. So you can have a 5 to 10 kilohertz field and it can be spot on for this and way off for this. So it isn't just like, let's be more complete. It's like, let's think about this offset thing and see if we can direct the magnetization down one branch or another. So we'll have a little bit weaker fields and a little more control over the spin transfer. So that's the motivation behind this section. Now, this is just repeating the old one, is it? No change. But I think we do have to change it. And hang on just a second, where did I put it in? Okay, yeah, it's coming up. That's why it's not in there. Now I'm just reminding myself that this is the point in the lecture where I finally put the magic angle spinning in. So I just decided to add these two pieces of complexity in one step. So we have been looking at expressions for the static or maximal dipole coupling in all the slides up till now with no MAS. And I actually want the instantaneous time-dependent value, including MAS, and I just take that static value and multiply. This is the result of what we did 2 weeks or 3 weeks ago. So we're also going to plug this in. So putting the MAS in, we had really only these two non-zero terms. The homonuclear couplings look like this for either I or for S. But now they're going to have some time dependence also due to MAS. The homonuclear couplings, which we're trying to work with, look like this. So I would say already my argument that this doesn't really evolve was a weak one. And now it's a different Hamiltonian. So we should deal with it, but I don't know if we'll get back to that. I do think that in many of these experiments, that's a weakness. And these two Hamiltonian, they don't look the same. So in principle, you can distinguish between them, and there are pulse sequences that do. But I'm not sure that we'll really get to this because of the time limitations. It's important topic though. And then this one is the one we want to work with, and now it has not only, this is represents the average of the spin degrees of freedom. But we're going to have to average the spin degrees of freedom after the new way that we approach the interaction frame. But we're going to have this time dependence also tagged onto the end of it. All right, so what we're doing here, that's different from what we did yesterday, is that we begin in the rotating frame and we do this tilted frame transformation. It's a one time independent rotation of spins around y and by an angle given by this expression, arc cos of that. So what was in our Hamiltonian as an IZSC, because we haven't done the interaction frame yet, so it's still just IZSC, it now has to be changed into I gets transformed into both IZ component and IX component according to the cosine and the sine of that tilt angle. And if we're going to have both of them off resonance, you need to do the same thing with the S spin. But as I mentioned in a lot of experiments, we kind of just like this example that I was talking about, you're just going to put the nitrogen on resonance as best you can. So maybe you don't need to think about this complexity. Maybe you don't need it. So it depends on the experiment. Nitrogens, you know, there are lots of interesting side chain nitrogens. For example, if you wanted to start at arginine and walk back to its carbons, then maybe you really would think about all of this. And then all of that is still modulated by magic angle spin. But this still hasn't gone into an interaction frame. So now take the resultant on the last page, like here's after the tilt, and I have an IZ, and I also have an IX. Now I'm going to rotate around the new IZ. And so IZ is unmodulated by IX becomes sinusoidal modulation between X and Y. Okay, and the same exact thing will happen to the S spin if I want to include that. And the MAS is still on top of everything. That's what your Hamiltonian has now become in the tilted frame. A better treatment for chemical shift offsets. At this point, we have a pretty complex expression with all the geometric components in Cartesian. And there are 3 different sources of time dependence, because omega 1 for I, omega 1 for S don't need to be the same. We're going to learn what their relationship should be this time. And you have omega R, and you have 2 omega R. So now we have to rethink what it means to be at that Hartman-Honn match. And I find it helpful to collect terms that aren't on the basis of X times Y. I don't know what that means physically. It just seems to me like a lot of stuff to manipulate. And I would try to recognize expressions for raising and lowering operators instead. This does correspond to taking the problem back to spherical harmonics. And so this is the point at which you could say, why maybe we could have done this whole problem with spherical harmonics, and might have been a good idea. Somehow the beginning of the problem always looks better Cartesian, and once you get into the halfway point or towards the end, you're like, no, I need my spherical harmonics. So a zero quantum operator, the way we write them in terms of raising and lowering operators is this. It's I plus S minus plus I minus S. And that does mean that IX is given by this, IY is given by this, I plus minus is another designation, and it would be IX plus minus IY. IXSX is all this stuff. IXSY is all this stuff, and so on. So I've worked these through and made a table for you, but let's notice that each one of these terms that's showing up for us, that's just two Cartesian components for the two spins glued together, in general, has zero quantum type operators in and double quantum type operators in, and there are no like Zeeman or zero order terms. They're not in. Okay, that's each one of these is like that. And I think what we want to do is to pick out where the zero quantum terms are and what their time dependence looks like. At least that's the strategy I picked here. Now, just to say once again about this tilt and this that first frame transformation to go to the tilted frame. If you're on resonance, so basically there's very little offset and B1 is quite strong, you will effectively have a very strong coupling because these tilt projection here, they're close to 1. And if you're way off resonance compared to a really weak spin lock, this comes close to 0 and you don't have any coupling. And in between, which is the case for experiments like we were just talking about, you'll have a value between 0 and 1, and that's what I use the term projection factors. It's a scaling of your dipole coupling you should be aware of when you set up the experiment. Sometimes you get lots of magnetization if you come off resonance for both of them. You just walked into another local minimum. But you should remember this moment from this lecture, like, yeah, I probably am having a weaker coupling, and I therefore probably will have more losses due to R1 rho. So if I have the time, I should probably find my condition closer to on resonance. Also, the projection factors should be not time dependent unless you're doing a ramp, right? Then you're going, you can vary the strength. You can also do ramps that vary the frequency of the pulse, and both of those will be like tuning up your projector factor. I don't know that that's useful to do, but maybe it's good to be aware of it, that that's happening. And the middle point of your sweep is usually where you're trying to hit the condition. So it would be that point in your ramp that you would compute what you think your projection factor is. Okay, that's just a side comment. Now, back to what we were doing. Of that long expression with the IX and the IY and so on and so forth, I pulled out the terms that contribute to zero quantum. So the I plus S minus and the I minus S plus terms. And they, of course, retain the MAS expression, no change. It turns out they had a factor in front of 1/4 for that conversion. And they have these cosine and sine terms. So there were two terms that resulted from that rewriting. And one of them has two tilt expressions, both sines at both angles, and then it's a cosine term in terms of omega-1 I and omega-1 S. Then the second term had the same tilt projection factors, but it was a sine term. That's what came from asking in that long Hamiltonian that was in Cartesian, which parts can be rewritten as zero quantum operators. So this is not the whole Hamiltonian, this is just a subsection. Also, might have noticed that Hamiltonian has, like, I'm going to decompose it into 4 parts, and it had, what's the last time it was all written out, maybe here? So these are all real expressions, I, X, I, Y, S, C, S, but when we rewrite them to the double quantum and single quantum, you get real and imaginary parts, so that those operators have a phase associated with them or are written in complex numbers when you rewrite in terms of raising and lowering operators. And what I decided to do is same slide, was it just on here, this one? Is to pull the real zero quantum operators first. So these are just the real terms. So there are two zero quantum operators, two double quantum operators, a real and imaginary. This is just a real. Now, if you look at these time-dependent terms, cos omega 1 for I, cos omega 1 for S, and then for this term, the only other time dependence comes here, cos omega RT, cos 2 omega RT. It turns out that this will be non-zero for a modified Hartmann-Hahn matching condition. We have to think about this additional oscillation, and the right combination of frequencies that make this have a non-zero overall average is that omega 1 effective for I has to differ from omega 1 effective for S by n omega r, where n could be 1 or 2 for the dipole coupling or 0 for the J coupling. I didn't include, but I'm just telling you that that's true. The J coupling condition. But that's not really a zero quantum operator, so maybe it doesn't belong on this slide. So that rule can be seen more clearly, I think, in the next slide. If you convert those sines and cosines into their exponent correlatives, but it makes the expression even longer, so that's pretty horrible. But then you can see what we're trying to do is have a match of terms that are multiplied. So here's the omega 1 oscillation, the omega 1I oscillation, the omega 1S oscillation, and the omega RT oscillation. So each term will have one of each of those. And what we'd like is that some combination of one of these two times one of these two times one of these two has e to the 0. That's what we're looking for. And that's a kind of easy way to realize where your matching conditions are going to be. Where are you going to get something that has a non-zero average? So the 2 omega r, looks like I only have the omega r term here, but I should have the 2 omega r term in here as well. Where is it? Yeah, it looks like I only pulled the 1 omega r term. It's just too long to put all of it on one slide, but you, on top of that, you're going to have another term that looks like this, that would have 2 omega r. And the exercise is to find, omega 1, omega 1I, omega 1S, and omega r, such that the sum of the three of them gives you e to the 0. And that is true when you hit one of these matching conditions. Does that make sense? So you need a time invariant resultant of the multiplication. So this page only illustrates for n equals plus or minus 1, but you could write out another expression with cos 2 omega RT, and then you'd get the n equals 2 conditions.
I have a.
Yeah.
So if I'm cross-polarizing from proton to carbon, am I usually able to reach powers that are able to excite the entire, like, very low offset for the entire width of carbons in my sample?
This is an important issue at high field. So let's talk about 400 megahertz first. So 400 megahertz, you want to cover 200 parts per million, and it's 100 hertz per part per million at a 400 megahertz instrument. So that's 20 kilohertz width.
Yeah.
For the isotropic shifts, they're all contained with them. And the power that you want to cover that would be, I mean, you'll have some off resonance effects if they're the same order, so you'd like the power to be a bit
Yeah.
larger.
Yeah.
So 40 kilohertz is a quite reasonable thing. Probes for lower field magnets, especially if it's a smaller rotor, have been optimized for so many years, so you could do that and cover it. If you now go to 800 megahertz, and yeah, so that's double. And do we want to be using 80 kilohertz pulses day in, day out? Probably not. There's another issue that whatever you're using for the carbon, generally the proton in the old school way of running experiments would be the higher of the two. So what's your spinning frequency? So you're putting your carbon at something like 80. Spinning frequency might be at least 20, if not higher. So now you got to think about the power handling on the proton side. So alternative matching conditions have been used. And we're going to see one with the double quantum term in just a minute. You know, so that you're not always pushing the probe to the extreme. But if you do something to reduce the carbon bandwidth, carbon power, carbon Rabi frequency, then the issue that you raised is going to come up. You're going to be preferentially cross-polarizing, like aliphatics versus carbonyl. Many of the carbons that show up above, you know, even 60 ppm have significant shielding anisotropies. And if you match a spinning sideband of that carbon, I think you will expect some magnetization to be picked up. Will it be less representative of the whole powder ensemble in practice? Doesn't seem like that's really a thing. You might think that it would be, but actually, you know, there's often people bias a little bit towards the middle of the spectrum or towards the aliphatics in their choice of carrier. And then maybe that overlap of the CSA from the carbonyls is enough. And another issue with the carbonyls is that they don't have an attached proton. So overall, you'll see a lot of experimental conditions or published spectra where the carbonyl doesn't seem to be fully optimized the way the aliphatics are in terms of like relative intensities of the peaks. In the modern experiments that are like triple resonance, this is less important because the step, if you approach it along the lines of what we talked about here, you're moving from the emitic proton to the nitrogen and over to the carbon. So these issues then go away. Yeah, so it's kind of, it's a dual problem, like your bandwidth question, but then I immediately combined that question with questions of power handling. And then there's also adiabatic sweeps during the CP, even for that first step. And they solve a myriad of problems, not just the one that you mentioned. Or sweeps, even if they're not properly adiabatic, but sweeps. Okay, so those are our matching conditions. Why am I returning to this? I don't know. I don't need that slide there. Now, there are also imaginary zero quantum terms. I'm sorry, the font is so small. These expressions get quite long, but the imaginary zero quantum terms result, you know, from different Cartesian components in that first expression. But they are absolutely analogous. They have, each term has some projection factors and then some time dependent factors that depend on the same three, omega 1 of I, omega 1 of S, and omega R of T, as well as 2 omega R of T. And they end up being preserved for exactly the same matching condition. So in a sense, it wasn't important to separate the imaginary and the real parts of the zero quantum. Maybe that's a little bit of an artificial distinction. So both pieces of the Hamiltonian and the zero quantum operate with the same matching conditions. On the other hand, if we gather up from the Cartesian expression everything that it converts over to a double quantum term and convert it, we get the following: omega is d max, geometric vector of a quarter, the real double quantum operators, and then these time dependencies. So it's the same frequencies at play, but there's an important difference. So the cos and sine terms are organized such that it's the difference between those two frequencies that needs to match n omega r. I'm sorry, it's the sum for the double quantum that has to match n omega r, whereas in the last slide, we saw the difference has to match. So for Hartmann-Hahn, remember that before we had any magic angle spinning, our idea was just to set them equal to each other. So that would be omega 1 I minus omega s is 0. That was our first idea. And that corresponds to the rotor frequency being 0. You put the MAS in, and you would think of this maybe being the modified condition. Their difference frequency is now the MAS. But actually, this condition also preserves magnetization transfer, but it's different kind of operators. And that has a consequence for your spectra. That with a zero quantum operator, I begin with x, and I end up with Sx of the same sign. And if I operate the double quantum by sitting at a different matching condition, I will end up with a flipped sign. And so if you do a broad scan, just phenomenologically, like just optimizing at the instrument, but taking a really, really broad look at different combinations of powers to see what signal you can get, you'll see both of these conditions, and you'll see that change in sign. And you'll also see something called a J-based transfer, where n is 0. In other words, you go to the Hartmann-Hahn as if you weren't spinning, because the J has no modulation frequency. You'll see all of them. So in summary, zero quantum matching condition is met for that equation, the difference frequency matching a rotor frequency or a double. And you have a conversion of Ix to Sx, double quantum matching condition is regards the sum frequency. And so that could take you to much low, let's say you're really fast spinning. This is an important thing to be aware of also for very fast spinning. It may be impractical to set up a difference frequency equal to omega r if omega r itself is 100 kilohertz, so very fast spinning, right? But you could set up a situation where their sum frequency is 100 kilohertz. So this is an important condition to be aware of for ultra fast spinning. Yeah.
Is it reasonable to anticipate a difference in transfer efficiency between zero quantum and double quantum conditions? Because
I think the factors are the same.
well, I was thinking about whether the coherence generated might have different relaxation rates in rotating.
Yes. Yes. So even though your target is Ix, or your source is Ix and your target is Sx in both cases, if you think the way we were talking about earlier in class about those commutators and double commutators, you're moving that by way of zero quantum coherences or double quantum coherences. And there's reason to expect that those would have quite different relaxation times. And there's been a little bit written about that. We did a little study on that. And there's some work from other labs. And one of the things that might be the case is that, you know, if dipolar phenomena are the dominant contributors, modulation of conformation, but through which Hamiltonian term? Maybe your first guess would be protons and dipole couplings is the dominant. Then you would think that there's some correlation between a carbon and the next carbon over. They have some of the same proteins in their protons in their environment, and they participate in the same low frequency modes. And then you would think if they're modulating together, they're correlated, then maybe you don't really get very much zero quantum relaxation from that, and you get a lot of double quantum. So you could expect that they're not going to be the same, but I don't think there's any maybe go-to problem where it's really been solved all the way through. A more practical issue is that the conversion for like if you wanted to look into that, the conversion to create zero quantum coherences or double quantum coherences, those pulse sequences, which we haven't talked about next, they have different efficiencies. Like you can't convert perfectly for the case of the zero quantum. So studying it has a little challenge inherent to it. Other practical considerations for transferring. I think the projection factors are the same. I think those numerical factors are the same. So probably a small difference in the relaxation would be the main thing. But what fits into your hardware is usually the most important consideration. So for many lower moderate field, lower spinning, we've always been doing the zero quantum. It just this corresponds to some practical conditions for the spectrometer, and for the super fast spinning experiments, you'll often see. Now, the behavior of this, and this is a little bit what we chatted about during the problem session yesterday. The behavior of this pulse sequence, theoretically, you would think it would depend a lot on the crystal light angles, chemical shift offset, and of course the distance. These are some of the things that you would think would be important. But in practice, folks use very, very long mixing times, so the crystal light angles actually don't seem to matter as much, and longer distances are sometimes successful. But where the trouble might arise is on accidental misset, accidentally hitting other conditions. So I thought for the last few minutes of class, I'd talk about what I mean by accidentally hitting other conditions. Also, it practically depends on some features of the sample, the things that drive R1 row, which can be many things, you know, paramagnetic impurity, all kinds of things could affect R1 row. But in practice, a lot of times it's about the motion, which in turn is about hydration and temperature, like how much freedom do segments of your protein have. And that freedom results in a short R1 row, which might be interesting, but it also might defeat your experiment. Also, practically, it depends on homogeneity and stability of the RF, of the spinning. So this selective double cross polarization experiment that we've been talking about, that if you imagine you're starting from nitrogen to carbon, it's demanding on the instrument, especially if it's not one bond, especially if it's like a two bond. It's a good test of an all-in performance. You have so much RF power on that you need so much stability, like to see if you can get a consistent experiment overnight, consistent enough to start taking 3Ds. It's a demanding experiment. So that's a little bit some of the stuff we talked about yesterday, but just summing it up. Now, I thought I might end up ending a little early today, but just talking about what I mean by other conditions. So you have a matching condition that you want to hit. But are there other constraints on your choice of omega R, omega 1, and omega S? These aren't the only constraints. I mean, there's the hardware, and there's something that I don't think comes up in the next slide. Let me just check. I don't think so. But well, It's already there in the slide. Yeah, no, I don't have it. Okay, so when we have talked a lot today about the range of carbon chemical ships. CO, C alpha, when you have uniform enriched samples, they'll have a 2 kilohertz coupling between them, which is not small. And they happen to have a change in chemical shift of about 110 ppm, something like that. 65, 175 wouldn't be unusual. And that parlays to I'll keep it in ppm maybe. Parlays on a 400, you could talk about 11 kilohertz. On an 800, you could talk about 22 kilohertz. But I often think about it in ppm, keep it in ppm in my mind. So one of the things that might come up is if you pick your rotor frequency, omega r dictates where you're placing your spinning sidebands, right? And if I pick omega r is about 110 ppm, then I'm going to see that my C alpha region in my spectrum is cluttered with CO sidebands. That already is a little annoying, just the spectral coincidence. It's going to be very distracting when you're trying to do your assignment and your peak peaking. 1D, 2D, or 3D. It's just a problem you're not going to enjoy. But in addition, the fact that they are coincident, a spinning sideband of the carbonyl is coincident with a C alpha does mean that they can exchange magnetization very readily, like on a 2 millisecond timescale, short timescale. So that's been referred to as a rotational resonance or R squared condition. And we don't want to be on that because it's going to control, it's a problem of peak picking, and it's also a problem of controlling magnetization. There's not really a good way to turn that back off with pulses that I'm aware of. You can make the spinning sidebands become invisible. There are pulse sequences for that, like during the detection period, but you really can't interrupt that recoupling very easily by user-friendly sequences. So you'd rather move to a different spinning frequency, and if you need to recouple those two carbons, do it with a pulse sequence. So that's the first thing, is that we look for spinning frequencies, omega r, of about 85 ppm. 42 works pretty well, but it's rare that you really want to be that low, or much bigger than, let's say, 130 ppm. In fact, it's better to be much bigger, like 150. Okay, so there are some constraints for proteins. Now, how does that parlay for nucleic acids? You have aromatic neighbors, and spinning faster is what you want to do when the isotropic shifts are close to each other. Just get the smallest rotor and spin as fast as possible. But you also maybe have that glycosidic linkage. You might really want to be able to look between the adjacent carbon to the nitrogen and then over to a aliphatic. But those are directly bonded, so it might not create the challenge that this does. So there may not be a corresponding, right? Because you either have sugar, or you have aromatic. And either way, the only thing you'd really be thinking about is that probably what's been fast. You don't have an aliphatic aromatic direct bond, right? Am I right? Oh, the methyl groups.
Yes.
So you don't want, and that condition you would hit at more like 140 ppm. That would be a place you might want to avoid. 140. And if you were working on a nucleic acid protein complex, then the islands would be 85, but a great preference to more than 160. That would be really that complex. which maybe we will soon in a collaboration. So that going into it, we do have favorite spinning frequencies. So we have rotors that can go in different ranges. Some are best for low speed. Some go all the way up to above 60 kilohertz. But not all ranges are actually spectroscopically desirable. So we like to be at 85, above 130 for a protein, and maybe for these complexes with nucleic acids above 160 or so. Now, there are other rules, though, about the match of field strength to rotor frequency. So this has a strong analogy to what we talked about with the dipole coupling. If omega 1 equals n omega r, then the average of the chemical shielding tensor, the time average, is non-zero. And the chemical shielding, even though it should just form those nice spinning sidebands, it actually evolves in a different way and dephases, and you basically lose all your magnetization. So you reintroduce the CSA very strongly. This is the name of a solid state NMR spectroscopist out of Utah, University of Utah, Salt Lake City, and he discovered this and wrote a nice paper about how it works. Some people refer to this CS condition as rotary resonance condition, and some people call that R cubed. So there's lots of different jargon about this condition, but it's not a good place to be unless you're doing something exotic. You do not want to match either of your field strengths to omega R. I didn't figure we have time today to properly do the theory of this, but you can think this way, that if you just have a CS Hamiltonian, it looks like this, right? During a spin lock, what would have been an IZ type chemical shift Hamiltonian, if you're talking about a minus X pulse or X pulse, it has become a Hamiltonian whose oscillatory behavior goes between Z and Y. Got an X pulse, okay? Now, at the same time, you're doing this spin, okay? And that means that your time dependence really has two frequencies in it, just omega 1 and omega R. So that leads to a condition where you have both of these operators quite active, not just rotations around Z, but effective rotations around Y. That leads to diffusing your magnetization through a whole sphere. It's kind of like a hand wavy description of what this is. So yeah, here I did mention this, but I didn't really explain it. Delta omega iso, so the difference between our carbonyl and our C alpha over there on the board. Delta omega iso is omega R. That's another condition. It's transferring magnetization between CO, C alpha, and the CS condition is just, I call it hosing. You know, you're just gonna obliterate anything with a large CSA. Maybe it's useful if you just want to see your methyls, but most of the time it's very, very annoying. So those are two more conditions that you wouldn't want to do on accident, right? And then there's something called the horror condition. That's an acronym from the Nielsen lab, Nielsen's lab. It refers to a situation where omega 1 is half of omega R, and you have homonuclear couplings, and they can evolve very strongly. So it isn't a great place to be, but I've seen that sometimes to avoid the CSA conditions, people go there, but you actually don't really want to be right on that. What's happening there is the dipole coupling has an omega 1 I dependence, for example, and you have 1 and 2 omega R. And so you can recouple not just at what I call the CS condition, but also at this horror condition. You can reintroduce homonuclear couplings. So I use the phrase a minefield of matching conditions. Just you've got to be aware of where you are, what you want when you pick these. And I think it's even not excessive to take and write a spreadsheet. Like if you're optimizing and you're calibrating and you're trying to decide what field strengths to use for the first CP and the second CP, something that will just automatically check if you're close to one of these unwanted type conditions. So here's omega I effective, and here's omega S effective. And I wrote it as a ratio of omega R. So the way I think about experimental design, you pick omega R first. You say, okay, what hardware do I have? What headaches do I want? What, you know, so where's omega R? And just pick that first. And after that, you say, well, which of these are experimentally possible? Which ones will Eric Killer let me do? Okay, and same over here, okay? And so you might not be allowed to do 3, okay? But so now you have a grid that's wide open. But now you start putting some of these unwanted conditions in. So you say, I don't want a horror condition here and here. I want a CS condition. So this is this is not allowed. Red lines are not allowed. Now, to do my transfer, I have to be on one of these diagonals, but I need to be far away from the red and the purple. So I think, you know, you can do the same thing that I've done in a graphic. You can do it in a spreadsheet, but it's not good to just do it in the back of your head. Like, oh, I forgot. Like, that's not good instrument usage. So practical with the hardware. Practical with the hardware. What else did I want to say about this? These conditions, whether it's 3 halves or 5 halves, you might find that you have different projection factors as well, so they might be theoretically better or worse. But here are 2 places that might work well quite often. And we refer to this as the 1.5, 2.5 conditions. 2.5, 1.5 conditions. So if you needed to go lower for some reason, you just maybe want to be a little bit off of that exact half situation. I feel like there was another point I wanted to make with this, but I can't remember what it might have been. Lost it. Anyway, I thought that might be a good point to end. You know, topics that we could continue on to, I sort of listed last time, things that we can think about having more discussion if we have another session later in the term. Yeah.
How does record handle the rotary resonance coupling?
So rotary resonance recoupling, R3 CS condition. Let's go back to that slide. We were always trying to stay off of it in the sense of picking field strengths that were, you know, half integer related to omega R. So not being at omega R or 2 omega R. So initially, we weren't thinking it was going to be such a problem, but a couple of things. One is that to reinforce something I was talking about yesterday, if you say I'm off or on a condition, this cartoon should be modified in the following way to be to tell the story better. Let's say we're talking about horror conditions. Are they razor sharp? Do you remember what we talked about yesterday? Like, is it that if I don't exactly match it to 4 significant figures, I'm off the condition? Do you remember what we said? I think if there's one thing you remember about these conditions, this is a good one. And I'll try to rephrase what I said yesterday so it'll stick better this time. The conditions all have a characteristic width. You do not have to be spot on. And the characteristic width is mainly determined by the strength of the coupling of the thing that you're trying to bring back. So if it's a very weak coupling, then you got to really hit it. You got to really nail it. So if you're trying to do DCP for a long distance, the ramp is essential because you're not going to be that precise. if you have a short distance, then you should be aware that that condition has width. If it's like 2 kilohertz or 10 kilohertz, it's hard to get off the condition. And the CS conditions, let's say you're talking about an aliphatic, they might have 5 kilohertz of width, probably live with that. Like if you put numbers on these that are in kilohertz, this might be 20 and 40. Where are my CS conditions? They're red. So if this had a width of 5, the unallowed regions are not this sharp line. It's a width that you could see here. And I think it would be an improvement maybe to the slide if I try to put that in, what I think the width of each of these is. But it's mainly determined by that. There's also experimental drift and so on and so forth that influences this, but the inherent width is like a fraction of the coupling, like a quarter of the coupling, or half of the coupling. Now, for the CS condition for a carbonyl is like 20 kilohertz or something. So it's starting to cover the whole thing. I mean, it is stronger when you're on, but it's never fully off until you get way up here. That's a problem. So what goes on for that condition, just sort of qualitatively explained here, even if it's not beautiful and geometric, it is actually deterministic. You're evolving under a Hamiltonian with deterministic rules. It isn't Redfield theory, right? We're not talking about dissipation. So whatever it is, we should be able to recouple it. And if we don't want to simply spin way up in a 100 kilohertz regime, if we want to stay at moderate spinning frequencies, just to explore how they work, then we're going to have to make this, if it unwinds, we're going to have to get it to return where it came from some other way. And so we started to think about putting extra pi pulses in, and those shouldn't affect the dissipative terms, at least not very much. And they helped a little bit. But what helped more was phase cycling the spin lock itself. And you can, take this low order theory and see how that might work. That if you phase cycle like the X pulse and it's unwinding along Z, that bit might return nicely just with the MAS. But the Y part, maybe not. Maybe it just keeps wandering off and it doesn't commute with the Z. So if regularly we force that Y, we change the sign of the spin lock and force it back up, then it will persist longer. I think the numerical simulations there were very important because I don't think we're in the right regime comparing the coupling and the spin lock to truncate down to just one term length. It's a bad example for using the average instead of the effective Hamiltonian. So we got a lot more guidance from the numerical simulations than paper and pencil type arguments. And maybe if we'd taken we just did start to take more terms, and maybe if we worried more about those terms, we could have done it the old school way. Yeah, that's the idea, is to sort of refocus all this wandering off the XY plane.
But if I just take the first term in the matrix expansion, just the average Hamiltonian, then I can't see a width. It's inherently a second order effect that matching condition will be.
To explain the width, I guess so. I'd have to think about that. I used to have a slide explaining why the coupling is the width of the condition, and I'm having trouble reconstructing it just standing here right now. I think it would be a good thing to expand more on here. Yeah, I'm not sure if I put some of that in the notes or not. You can look around at that. But I think you can think about it as being another term that's orthogonal. I think that's probably right. I think that gives you the width. I'd have to recollect how I presented that before. Yeah, good question. Other things? Little less of a breakneck pace today, like sort of fit into the allocated time, interestingly enough. Okay. So, I was starting to say, we might have a chance to do some of the other topics people have asked about. Later in the term, I'm not sure, or maybe that would have to be, after the semester ends. So just be thinking about that if there were some of those, we mentioned quadrupoles.
DNP.
We mentioned DNP, we mentioned dynamics, we mentioned other recoupling sequences where we might come back and touch on some of these points in more detail. So I think we could do one or two of those if we wanted to. We might take on the question of nucleic acid applications specifically. Could be fun. So just be thinking about, you might be burned out by May, but we'll see.
Thank you.
Yeah, thank you. It's nice having you guys here.